So looking at each of those vertical asymptotes, how can we tell from the equation where they are? In each of them, if you plugged in these values, what would happen? You'd divide by 0. And so each of those vertical asymptotes happens at a place where we have a non-permissible value. So that's the first thing that we looked at. Now you might remember in each of these cases, if I labeled my horizontal asymptote, I'd get y equals 0. You might remember from grade 11 that all of your 1 over graphs have an asymptote at y equals 0. We're going to look at this year some other asymptotes, some other places. So in this math lab, what we're going to do is in the construct the understanding part, you're going to set your window to negative 9.4 to 9.4 and negative 6.2 to 6.2. This is called the friendly window. The friendly window sometimes will show things that other windows don't. And what you're going to do is for each of these functions, you're going to sketch them with your graphing calculator, label any vertical and horizontal asymptotes, talk about any non-permissible values, and fill in this chart, and then we're going to go over them and check how you did. We are going to add some things to these graphs. So if there's a gap in the graph, draw an open circle and put arrowheads on the end just to practice that. If you see that there should be an asymptote, your graphing calculator won't draw in the asymptote because it's actually not part of the graph, but we can draw it in with the dotted line. So there's one there. We can label these at x equals 1. This one's at x equals negative 2. And this last one has a hole in the graph. Just add the arrowheads onto these. We're going to find out later that these two in the middle also have something called an oblique asymptote or a diagonal asymptote. But we don't know how to do that or what that is yet. But I'm just going to introduce that idea to you. So the question on these ones, and what I'd like you to do is look for a pattern. Notice that each of these equations has the following pattern. It has an x squared, so above the group 1, I want you to write that it has a degree of 2 on the top and a degree of 1 on the bottom. So this is our pattern that we notice, that each of these functions is like an x squared over x, a parabola divided by a line. And the characteristics that we get when you have a parabola over a line is you either get holes in your graph, some of these had holes in the graph or points of discontinuity, or the other option, if it doesn't have a hole, is you have a vertical asymptote and an oblique asymptote. So these are the patterns that come up. Either we're going to get holes in our graphs, or we're going to get vertical asymptotes and also an oblique asymptote. So the question is, how do we know if there's going to be a hole or not? How do we know when a non-permissible value, because sometimes our non-permissible value is a hole, and sometimes our non-permissible value is a vertical asymptote. So how do we tell? Well, the way that you tell is through factoring. If you would take this original equation and you would factor it, can you see that you would get bracket, 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 a difference of squares, x plus 1, x minus 1, divided by x plus 1. Once I factor it, what could you do with that? You could simplify, right? The x plus 1s would cancel. Anytime a non-permissible value cancels out, because what does this change to now? Whoops, I don't want to write in red. If I cancel that out, I just get x minus 1. How do you graph x minus 1? It's a line, right? Y-intercept of minus 1 and a slope of 1. Can you see that that's the line that got graphed? The only difference is that minus 1 is still a non-permissible value. And so you graph the line and you just put a hole where the one non-permissible value is. And we can even label this hole. This hole, we know the x value is minus 1. And now that I know what the actual equation is, if I plug minus 1 into the simplified equation, minus 1 minus another 1, the coordinates of that hole are minus 1, minus 2. So when we graph these later on, you're going to be asked to graph them. This would be a non-calculator question, and you would be asked to label where that hole would be. So if we can factor, and one of our factors or one of our non-permissible values cancels out, that will always result in a hole. In fact, you can make an x minus 1 graph with a whole bunch of holes, right? Because if I took this graph and I added x plus 2 and divided by x plus 2, I'd make another hole. And then I add x minus 3 and divide by x minus 3, that'd make another hole. And I could draw a straight line with like 15 holes in it if I wanted to. Because every time something cancels out, it makes a hole. Okay, I'm going to get rid of that blue because that was just being distracted. So let's look at the other ones that had holes in it. If it has a hole, it's telling us chances are we can factor this. So can I factor the top of this one? Yes. I get x plus 2, x minus 1. Are there factors that are identical? Yes. And so those cancel out. And so this too just becomes the line x minus 1. And I know that I'm going to have a hole when x is equal to negative 2. If I want to know what the y coordinate is, I say to myself, well, since this simplified to be just x minus 1, when I plug in negative 2, I'm going to get negative 3, and that's where the hole is in that graph. The last one that has a hole is the one at the bottom here. Again, if we factor things out, on the top I could factor out a 2x, leaving me with x minus 2. And I have an x minus 2 on the bottom. So since these cancel out, that tells me there's going to be a hole. There's going to be a hole at 2. And since the equation simplified to just be 2x, that's why we get that line. If I plug in 2 into 2x, I would get 2 comma 4. That's where my hole is. Now the middle two, if we look at those equations, they can't be factored, or in the case of this one, it can be factored. It's x plus 1, but it doesn't cancel out. The factors aren't the same. So in those cases, your non-permissible value stays as a vertical asymptote. And we're going to learn later how to find that oblique asymptote that goes with it. And we're going to find out later how we would graph that completely, because that's a weird looking graph in the end and one you haven't seen before. So this is group 1. A parabola divided by a line. What do you get? And when you take a parabola divided by a line, the characteristics are sometimes you get holes, sometimes you get vertical asymptotes. It all depends if your non-permissible value cancels out. So go to group 2. These ones are lines divided by lines or parabolas divided by parabolas. There are the graphs, and again, we're going to add our asymptotes in here with a red pen. So you have a vertical asymptote at x equals 1, and there's a horizontal asymptote, y equals 3, x equals -2, and x equals 2, y equals 1. X equals 1, y equals -2. So group 2, how are we going to describe group 2? Well, these are either lines over lines or parabola over a parabola. We can describe group 2 as having the same degree divided by the same degree. And by the same degree, we're looking at the highest power. So the highest power degree that you find in your numerator and the highest power degree you find in your denominator. So either it's parabola divided by parabola, it doesn't matter if there's extra x's in there or not. You're just looking at that. So the question is, what are some of our characteristics? Well, our characteristics for these ones is it has both vertical and horizontal asymptotes. Again, sometimes these groups are going to get mixed together. So we're still going to check, is there anything I could factor? Because if there's something I could factor, maybe one of my factors cancels out. For example, in the second one here, can you see that the top is a difference of squares and the bottom is a difference of squares? So we could have x plus 1, x minus 1 over x plus 2, x minus 2. But since none of those factors cancel out, we have no holes, and any non-permissible values that you have that aren't holes will always show up as vertical asymptotes. So our vertical asymptotes for group 2 are the same idea as our vertical asymptotes for group 1. If you have a non-permissible value that doesn't cancel out, it becomes a vertical asymptote. How do we find our horizontal asymptotes? Our horizontal asymptotes can be found by just looking at your highest degree or your highest power. In the first one, it's a line divided by a line. The highest power is an x to the 1. If you just look at the x's and ignore everything else, can you see that you would get 3 x's on the top and 1 x on the bottom? If you have 3 x's on the top and 1 x on the bottom and you simplify that, you just get y equals 3. And that will become your horizontal asymptote. So if you have the same degree on the top and the same degree on the bottom, and you just look at your highest powers and simplify, that will become your asymptote. So look at the second one. What's our highest power? It's an x squared. If we just look at our x squareds, what do we have? We have 1x squared on the top and 1x squared on the bottom. If you simplify that, you just get y equals 1. And that's our horizontal asymptote. In the last one, what's the highest power? It's an x. We have a negative 2x on the top and a positive x on the bottom. If you simplify that, you get y equals -2. So our horizontal asymptotes are found by looking at the highest power in the top and the highest power in the bottom and seeing what that equals to. Now, a little explanation about horizontal asymptotes. They act a little bit different than vertical asymptotes. Vertical asymptotes deal with non-permissible values. Your graph never crosses a vertical asymptote, because that would mean it goes through a non-permissible value. Horizontal asymptotes tell you what's happening to the graph as it gets either really big positive numbers to positive infinity or really big negative numbers to negative infinity. It is possible at times that a graph passes through a horizontal asymptote in the middle, because horizontal asymptotes tell us about the end behavior. What happens when x gets really, really big, right? You have 3 million divided by 1 million minus 1. If you're dealing with really, really big numbers, right? So You happen across, you're at Walmart in the shopping line, and who's in front of you but Bill Gates, and he's buying some shampoo or something like that, and he drops $1. He decides not to pick it up. Why? How much money does that guy have? More than me, right? $1 billion. So he looks at his bank account and he says, if I have $1 billion and I lose $1, right? Does it make a difference? No. So that's our end behavior here. We have 3 times x. If x is huge, and on the bottom you have a huge number minus 1, what is that minus 1 going to do to that huge number? Not a lot. So that's why we ignore everything but the big numbers, just the highest powers. And that will tell us when x gets really, really big, 3 billion divided by 1 billion minus 1 is going to be really, really close to 3. And that's why that asymptote is there. Me, on the other hand, don't have a lot of money. I drop that loonie. I see some little kid reach for it. No way. Throw them across the aisle. Pick up my own loonie. Make sure that I keep it. So that's the idea behind the horizontal asymptotes. What happens when x goes to positive infinity? What happens at the end behavior as x goes to negative infinity? Okay, group 3. We are going to add our asymptotes again. First one will have horizontal asymptote. Second one will have a horizontal asymptote. We also have 2 vertical asymptotes. The third one has a horizontal asymptote at y equals 0 as well, and a vertical asymptote at x equals 0. Fourth one, horizontal asymptote at y equals 0. The fifth one, horizontal asymptote at y equals 0. So the pattern for group 3, what kind of equations do we have? Well, we have some constants over parabolas. We have lines over parabolas. But the key is in each of these, we have a smaller degree divided by a larger degree. So the polynomial that is in your denominator has a larger degree than the polynomial that is in your numerator. What happens every single time as far as a characteristic for this group? Sometimes we have sometimes we have vertical asymptotes, sometimes we don't. But a characteristic that we always have is we always have a horizontal asymptote at y equals 0. Now, why does that happen? We can use the same idea that we used for group 2 to find our horizontal asymptote. So in group 2, we found our horizontal asymptote by looking at the highest degree. If we look at the first function, the highest degree is an x squared. We have, if we ignore everything else, we have 1 x squared on the bottom. How many x squareds do we have in our numerator? None. So we can write that we have no x squareds in our numerator. And if you simplified that, you're going to get 0. The idea is as follows. Again, it talks about end behavior. Horizontal asymptotes talk about when x gets really big, either positive numbers or really big negative numbers. Okay? So our first example. It's your birthday. You have 6 birthday cakes you want to share with all of your online friends. So you go to Facebook and you realize that you have 3,505,000 friends on Facebook. And you want to share those 6 cakes with all of those friends. How much cake is each person going to get? So you take out your knife, you carefully measure, and you divide all 6 cakes so that you get 3,505,000 pieces. How big are those pieces going to be? I guess it depends on how big the cakes are that you bought to begin with, but if they're regular size cakes, they're going to be tiny, very small. So the idea is everybody's going to get next to nothing. The next day you don't have any friends on Facebook. They've all defriended. Is that the correct word? Unfriended? Unfriended is better than defriended? Okay, I like defriended, but disfriended. There's got to be. Okay, unfriended. Anyways, when you divide by a very, very big number, you're going to get closer and closer to 0, especially as x gets bigger and bigger and bigger, right? You put out a thing, everybody is invited to my birthday, and it goes viral. The whole world decides to show up. Well, you'd have to split that cake up by, what, 6 billion, 7 billion people? Everybody's not going to get very much. It's going to be the worst party ever. But it is going to be awesome to open all those presents. How many years would that take you? A long time. Then you have to worry about returning duplicates. Oh, it's just not worth it. Okay, so we get an asymptote at y equals 0. Same thing in the second one. What's your highest power? It's an x squared. How many x squareds do we have on top? None. How many do we have on the bottom? A minus 1. What happens when you do 0 divided by a minus 1? You get 0. The next one, it's x squared again. You have no x squareds on the top. You have 1x squared on the bottom. Simplify that, you're going to get y equals 0. Careful with these ones, because you're going to be tempted to say you have 2 on top and 1 on the bottom. But the highest degree is x squared. You have 1x squared on the bottom. You still have no x squareds. Even though you have 2 x's on the top, you have no x squareds on the bottom. And finally, in the last one, same thing. You have no x squareds on the top and 1x squared on the bottom. That'll simplify to 0. So each of these is going to have an asymptote, horizontal asymptote at y equals 0. Whenever you have a higher degree on the bottom, that's going to happen. Some other things that we're going to notice. I'm going to just check. Do any of these factor nicely? Well, this second one on the bottom, if we factored this, we would get negative x and x, minus 3 and minus 1. Oops. And so the bottom factors nicely. That tells us our non-permissible values are negative 1 and 3. That's why we have vertical asymptotes at x equals 3 and x equals negative 1. Your graphing calculator doesn't always do the best job of graphing the entire thing, but you can have it go all the way up to your asymptotes in both directions. And this is what the final graph looks like. I want to point out that in this one, can you see that your x's cancel out? 1x on the top would cancel out with 1x on the bottom. So this equation is actually the same as this equation. Normally, when something cancels out, you're going to get a whole. Since x canceled out, we should get a whole at x equals 0. But since you still have x as a non-permissible value, that whole doesn't show up because there's a whole and an asymptote basically at the same time. The asymptote wins. And there's still an asymptote at x equals 0. And the last example shows us an example where our graph has a horizontal asymptote, but your graph goes through that asymptote in the middle. So there is going to be cases where you have a horizontal asymptote and it feels wrong to have your graph go through that asymptote, but that can happen because horizontal asymptotes just tell us what's happening at the far ends. As x goes to infinity or as x goes to negative infinity. Okay, so for the rest of class, look over part B, but then there's 3 questions at the end I want you to work on.